All right, so we're going to start chapter 5 today. I'll go through the notes, kind of talking through as I fill out the notes. And then if you guys have questions, you're more than welcome to ask them in class. So starting chapter 5, we're going to start talking about probability. Probability is the chance of an event occurring. So when we talk about this, we're going to be talking about probability experiments, which is a chance process that leads to well-defined results called outcomes. We don't usually use the term probability experiments, but rolling a dice is a probability experiment. Picking a card out of a deck is a probability experiment. Flipping a coin, probability experiment. All of those things are probability experiments because it's a chance process, rolling a dice. I don't know where it's going to land, and there's well-defined results. 1, 2, 3, 4, 5, 6, if it's a six-sided die. So that's a probability experiment. And then an outcome is a result of a single trial. So an outcome of rolling a die is the result of rolling it once, and then you record that. A sample space is the set of all possible outcomes of a probability experiment, and it's written in the brackets with the outcome of each event there. So let's go through these examples. Give the sample space for the experiment. So if we roll a die once, my sample space is 1, 2, 3, 4, 5, 6. If I flip a coin once, my sample space is heads and tails. Take a second and see if you can fill out the rest of these sample spaces. All right, so we've gone through, and you can see that I've filled out the rest of these. So flip a coin twice, heads, 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 tails, tails, heads, tails, tails. Flipping a coin 3 times, 3 coin flips represented. And then up here you can notice how I'm able to go through and check to make sure that I'm finding all of the different possible outcomes. So this number represents how many options or how many different outcomes can happen. And then the exponent represents how many times that event is occurring. So for a coin flip, there's 2 outcomes, heads or tails. And in this first one, it's happening twice. And so that's how I get 2 to the first power, which is 2 different outcomes. Next, for the coin flip here, you can see that I still have 2 outcomes, heads or tails, but it's happening twice. So it's 2 squared. That means there's 4 total outcomes. Here, still with the heads, tails, but now I'm doing it 3 times. So now there's 8 possible outcomes. So rolling the dice, this is all possible combinations. So 1, 1, 1, 2, 1, 3, so on. And again, I have 6 possibilities because there's 6 different outcomes of a dice, and I'm doing that event twice. So it's 36 total outcomes. So the sample space is 36 things. When I ask you for a sample space, you have to write out all of the things in the sample space. You cannot just give me the number of things in the sample space. And then lastly, drawing a card, a single card from a deck. So drawing a single card from a deck of 52, all of those are the possible outcomes. I could get the ace of diamonds or the 2 of clubs. It doesn't matter, but there's 52 different outcomes, and that's the sample space. Each individual card is the sample space. I suggest you understand and learn about the makeup of a deck of cards. You'll need to know that there's 52 cards in a deck. You need to know that there's 4 suits, that there are 13 cards in each suit, that there are 3 face cards in each suit. Make sure you know all of that information. If you don't, it'll make the homework more difficult. So as you're going through the homework, if you're having difficulty with that, make sure you study and you understand the makeup of a deck of cards. Next, we're going to talk about how to use a tree diagram to represent a list of possibilities. So we have our first flip. So the possible outcomes for my first flip are, I could get heads or I could get tails. That is my first flip. Now I have a second flip. Each of those heads, I could get a heads or a tails, and from that tails, I could get a heads or a tails. Now, I can use this tree diagram to come up with my sample space. as long as I start at the top and work my way through, I'll get a list of all possible outcomes. You can see starting at the top, working my way down, I come up with all 4 possible outcomes. And so this tree diagram is a way of helping write my sample space. So then after we've done that tree diagram, then we can write our sample space: heads, 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 tails, tails, heads, tails, tails. All right, take a second, pause the video, try and do this example here. Same idea, but now instead of just looking at 2, we're looking at 3. So write the tree diagram and write the sample space out, and then unpause when you're done. And so there we have our tree diagram with our first child, our second child, and our third child. And then after that third child, I went down and then just collected a list of them and then rewrote them in my sample space. That is what a sample space should look like. When you're done finding them, rewrite it to make sure it looks like that. Next, we're going to talk about an event. An event is a set of outcomes, and it's written as capital letters. So on the next page, we talk about the probability of A. So P is pronounced P of A. So P of A, that is the probability of an event, and that event would be event A. You could have P of F or P of E. Whatever your event is, whatever variable you've given to that event, when you put it in parentheses, we're talking about finding the probability of that event. So for an example, we have dice and we have our 6 outcomes, and we've found our sample space, which is 1, 2, 3, 4, 5, 6. And then we have different events. An event could be simple as rolling a 6, which contains 1 possible outcome, or it could be rolling an odd, which has 3 possible outcomes. It could be rolling a number greater than 2. Your event is just a list of different outcomes. And next we're going to talk about the first of 2 different ways of computing probabilities. And the first way is called classical. I will also refer to it and help you guys remember it using theoretical probability. So it's what the theory or what the probability should be. If in a perfect world everything was perfect, what is the probability? And the way we find that probability is the number of ways E can occur. So that's N of E. So the number of different events in our number of different outcomes in our event divided by the total number of outcomes. And that's how we find the probability of all of our things. So the next thing we have is we have a bunch of different card probability questions. So what is the probability of getting a queen? Well, first of all, we need to know how many queens are in a deck. There are 4 queens in a deck of cards. Then we need to know how many cards are in a deck. And we just did that as part of the earlier probability. There's a total of 52 cards. So 4 queens, 52 cards, which gives us a probability of 4 52nds, which reduces down to 1/13. So the probability of getting a queen in a deck of cards is 1/13. Next, we're going to look at a club. Well, there are 13 clubs out of the 40 or 52 cards, which means we have a 1 in 4 chance of getting a club. Go through and do that same process to find the probability of getting the rest of these outcomes. All right, so Next, how many black 4s are there? There's 2 black 4s. There's the 4 of clubs and the 4 of spades. 9 of hearts, there's only 1 9 of hearts, so 1 out of 52. A 3 or a diamond. Well, there are 4 3s, so 4 out of 52, plus, because we have an or, and we'll get more into that later, a diamond, and there's 13 out of 52, which gives us 17 out of 52. However, that is not the correct answer. If we go back up to our list of cards, if I say a 3, I've got those 4 cards. Or a diamond, so I circle those cards. What happened when I circled the 3s and the diamonds? That 3 of diamonds got circled twice. I'm counting that card twice, and it shouldn't be. So if you have a probability where there's overlap, and again, we'll get more into overlap in those terms in a second, we need to subtract the amount of overlap. So in this case, there's 1 card that's overlapped, that 3 of diamonds. And so that brings our answer to 16, which actually reduces it to 4/13. All right, next, find the probability, or you flip a coin 3 times, find the probability of different events happening. So what is the probability of all heads? Well, we have our sample space here, and we see that there's a total of 8 different outcomes. How many of them have all heads? Just the one has all heads. So 1/8. Next, we want to find the probability of 2 heads. So again, we know that there's 8 possible outcomes. Now we need to go through and look to see how many of those outcomes have 2 heads. Well, 1, 2, 3 of those outcomes have 2 heads. So the answer is 3. Now, a lot of people often say, well, what about all heads? Isn't that 2 heads? No, this is not 2 heads. How many heads are there? There are 3 heads. So if I ask for 2 heads, I'm not saying 2 or more heads. I'm saying 2 heads, and that's it. You have to make sure you're reading carefully. You can't make an assumption that, well, this has 2 heads. Well, it doesn't. It has 3. So you need to be careful about that and make sure you're reading the questions very carefully. All right, some rules of probability. So when we talk about the probability of an event, that probability is going to be between 0 and 1. It can be equal to 0, it can be equal to 1, it cannot be negative, and cannot be greater than 1. If an event E does not occur, its probability is 0. So an example is, if you roll a 6-sided die, a normal die that's 1 through 6, the probability of getting a 7, probability of 7, is a 0. You cannot get a 7 if that 7 isn't on the dice. Next, if an event is certain, that means the probability of that event is 1. So what is the probability of getting less than 7 in a 6-sided die? Well, that probability is 1 because every number on that dice is less than 7. And then the next one is the sum of all of the probabilities of the outcomes in a sample space must be 1. So as an example, we go through, we listed the sample space for a 6-sided die. That's 1, 2, 3, 4, 5, 6. We're going to find the probability of each of those outcomes. So that's a 1 in 6, 1 in 6, 1 in 6. All of those individual outcomes have a probability of 1 in 6, which means the sum of them is 1. So all of the outcomes of the sample space individually must add up to 1, and no individual outcome can be greater than 1 or less than 0. An unusual event, if we're talking about something that is unusual, 5% is our cutoff. So if something happens less than 5% of the time, we consider that unusual. Next, we're going to talk about the empirical method, which is like the experimental method. It is what the probability is based on actually running trials, actually doing the experiment a bunch of times and recording the results. So here we have the number of times E occurred in our trials, and then the denominator is the number of trials that we did. So suppose we have a board game with a spinner with 8 spaces, all of the same size. When playing the game, you decide to count how many times someone spins the number 5. At the end of the game, there was a total of 179 spins. 39 of them were 5. Find the empirical probability of rolling a 5. So we'll start off with E is equal to rolling or spinning a 5. So the probability of E is equal to number of 5s rolled over total number of rolls. So there were 39 5s rolled, and there were 179 total rolls, which gives us a 0.218 chance of rolling a 5. Is that unusual? It is not unusual because it is above 5%. All right. Next one, suppose you did a survey to determine if people like the new taste of a soft drink, and their results were as follows. So we have 15 people said they liked the new taste, 8 people said no, 2 people said they did not know, and so there's a total of 25 people. So if E is equal to person said no, and that's what we're trying to find. We're trying to find the probability of E. That means number of no's over total number of people. Which gives us 8 over 25 as our probability. Next, we're going to create our frequency distribution. Again, this goes back to stuff we did in chapters 1 through 4. So we have O, A, AB, and B blood type. And we had 21 people had O, 22 had A, 2 AB, and 5B, which gives us a total of 50 people. And then we want to find the following probabilities. So, probability of O-type blood is 21 over 50. Type A or type B, or is addition. So this is probability of type A or type B. Well, that means we had 22 people with type A plus 5 people with type B for a total of 27 out of the 50 people had type A or type B. So if for D we're looking at a person has neither type A nor type O, so not A and not O, leaves AB and B. So another way of writing this is the probability of type B or AB. And we know that there are 2 people with AB and 5 people with B, which gives us a total of 7 people that don't have type A or type B. Or sorry, that don't have type A or type O. And then the last problem, a person does not have type B. So, not AB means everything else. So, if we have a total of 50 people and 2 of them have AB, that means 48 of them don't have AB. And so that gives us 48 out of 50 people, and we always reduce so 24 out of 25 people do not have type AB. Same idea, different frequency distribution. This time we're dealing with the number of days stayed at a hospital for maternity patients and the frequency of that. So we had 15 people stayed for 3 days, 32 stayed for 4, and so on. A patient stayed exactly 7 days. Would this be considered unusual or not? So if a patient stayed exactly 7 days, that means we have probability of 7 is equal to 5 over 127. Probability of 5 over 127 is equal to 0.039. And yes, this is unusual because it is less than our 5% cutoff. All right, next one stayed less than 6 days. So, less than 6 days means 3, 4, or 5 days. So that means we need to add the number of people that stayed for 3, for 4, and for 5 days. And so that gets us 15 for 3 days, plus 32 for 4 days, and 56 for 5 days, which is a total of 103 out of 127 people. Next stayed at most 4 days. So that means less than or equal to 4, which would be 3 or 4 days. That would be 15 plus 32, which is equal to our 47 over 127. And then at least 5 days is greater than or equal to 5, so that gives us 5, 6, or 7 days. And we had 56 people, 19 people, and 5 people respectively, for a total of 80 people stayed at least 5 days. And then we divide those all by the total number of people that stayed. Next, we're going to talk about the law of large numbers. The law of large numbers is about how as the number of trials increase, the probability. All right, so law of large numbers states that as we increase the number of trials, the empirical probability will get closer and closer to the classical probability, meaning what happens in our experiments will get closer and closer to what actually happens in real life. An example is that if we flip a coin 20 times and we have 16 heads and 4 tails, in the long run, what would we expect the probability of heads to be? Well, right now, the probability of heads is 16 over 20, which is 8 over 10, which is 80%. So the probability of these 20 trials is that 80% of the time, heads is flipped. But if instead of 20 times I flip a coin 100 times, or 1,000 times, or 1,000,000 times, we expect that probability to get closer to the classical probability. And so in the long run, the probability of heads will be 50% or 0.5. So no matter what happens in the short term, given enough trials, we expect our empirical probability to get closer to that classical probability. And the last thing we're going to talk about in 5.1 is subjective probabilities. Subjective probabilities is simply a probability that you create yourself. It still needs to be between 0 and 1. You cannot have 110 as your probability. You can't say, I think that I'm going to get an A on this test. I think that's going to happen 110% of the time. That's not a real thing. That's not a subjective probability. It must be coherent, meaning you can't have two probabilities about the same event adding up to more than 1. So in the example we have is the probability of finding a parking space in downtown on a Saturday. You believe that is 0.2. You have a very low chance of finding a parking space. In order to make that a coherent probability, then the chance of not finding a parking space has to be 80% or 0.8. That will be the end of 5.1. We'll start 5.2 in the next video.